welcome to the first lecture of Thursday morning. We have Professor Sara Maloni, who will continue her second lecture on geometric structures of Anosov representations.
Thank you very much. Okay, let me start the timer. So welcome back. Thanks for coming to the second lecture. As Mike was pointing out, today there are more authors appearing because what I plan to do today is actually to work through two examples. One that we discussed with Daniele Alessandrini, Nicola Tolosane, and Hannah Wiener. And from that, with Filippo Mazzoli and Nicola Tolosane, we were thinking about the case of PSL3R. So in the first example, we did SP4C and the domain of discontinuity in the Lagrangian. Then we look at PSL3C, the domain of discontinuity in the full flag. And then my PhD student, Mason Hart, hopefully I will arrive to his work. He found a different idea about how to study the fiber. So if you remember what we did in lecture one, so what we finished discussing is the fact that when you have a component of an Anosov representation, if in this component you have a Fuchsian representation, then whenever you have a domain of discontinuity that is non-empty, you can look at this quotient. So we know by the work of Guichard and Wiener and Kovic, Lieb, and Porty that this manifold is a compact manifold. And what we prove is that this is a fiber bundle over the surface. On the other hand, I didn't tell you anything about how the fiber look like. And that's because in general, when we wrote that paper, we couldn't say much about the fiber. And so what we did in the second part of the work with Daniele, Nicola, and Anna was to study the fiber in one particular case, which personally I really like that part of the talk is because it's very concrete. So today we will focus on that example where we will study the fiber. We'll look at another example, and then we will say something more general about the fiber. Please stop me if you have questions. Wherever we will end up today, it's not a problem if we don't finish. So yeah, I think in the like the talk is like this talk today will be three parts: one SP4C, one SL3C, and one just general result. In fact, in the last part, even the last part will be split. So there is a different method for the case when the fiber is dimension 4, because Mason used Thor collection on simply connected for manifold to classify the fiber. And another idea when the fiber is a higher dimension, where using a different method, he can show that the fiber is a sphere bundle over a particular thickness. But we'll get there. Okay, so in the case of SP4C, I'm going to recall all this notation, but like in this case, we are looking at as the parabolic, the stabilizer of a line in C4. And so in this case, you have a domain of discontinuity in the Lagrangian. So the parabolic that we are using, they change. And so in this case, what we prove is that the fiber is homeomorphic to CP2 connected some CP2 bar. And the first time I was giving this talk, actually there was a friend that he studied for manifold. And so he asked me, it's like, do you know if it's diffeomorphic? Because actually the answer will be interesting either way. So if you answer yes, great. So you have a strong stronger result. But if your answer was no, it's actually even more interesting because it's not even known yet if there are exotic structure on these manifolds. But actually, with the work of my student, we can prove that it will be diffeomorphic. So with our method, we cannot say anything about the diffeomorphism type, and you will see why with the method that we are using. Any question? If you want me to recall more things from the past, just stop me. Okay, so first I'll give you the general idea of how the proof goes, and then we will go into the detail. And so the point of our method is to use the Friedman classification of four manifold. And to do that, we need to understand the intersection form on these four manifold. The way that we describe our fibration is actually not so easy to calculate the intersection form concretely. And so what we do is that we define another fibration that will not be smooth, but that will be much more concrete, and that fibration is really inspired by when we study the orbit of SL2C on Lagrangian, complex Lagrangian. Those fibers suggested us a way to project the whole Lagrangian space into H3 bar. And so in that way, we define a non-smooth, but more concretely defined projection where we can study the intersection form. And then since the two fiber from the two fibration would be homotopy equivalent, we'll conclude. Okay, so so we will see how we do that, but the big idea is that we build this other non-smooth fibration, which I think I call it Q here. So our fibration from our theorem is smooth, and I call it P. The other non-fibration, the other non-smooth fibration, Q, will have fiber FP and FQ, and they are both homotopic equivalent because they are homotopic equivalent to omega, because these are fibration over H2, which is simply connected. And so, as I was saying, this fibration is really coming from this study of the SL2C orbit, where we were able to identify the whole space of Lagrangian as ideal regular hyperbolic tetrahedra and their degeneration. So regular tetrahedra are tetrahedra of maximal volume, or you can also define as the cross ratio of the four vertices having one particular value that is symmetric with all the permutation. And so these maximal volume tetrahedra, they can only degenerate to line or point. So they cannot degenerate to a face because they are maximal volume. And so we identify Lagrangian with this space of ideal regular hyperbolic tetrahedra and their degeneration. And so there is a well-defined projection into the barycenter or the degenerate barycenter when you degenerate. And so this fibration, when you restrict to the fundamental domain, restrict to a fundamental domain in H3 union CP1 minus RP1, and then hence we then project down to H2. But I'll repeat that. But so let me discuss in more detail this example. As we did the last time, so we consider C4 as a homogeneous polynomial of degree 3 in two variables, x and y. We can define the symplectic structure that we are using very concretely in terms of polynomial. Like this idea of using polynomial is coming up nicely when you want to define the irreducible representation of SL2C in this case sp4. And so what you do is like you pair x3 and y3 and x square y xy square in this way. So it defines a symplectic form on C4, and the symplectic group is really really correspond to sp4c. So what we consider is Lagrangian, that are these maximal isotropic subspace. So an isotropic subspace is a subspace of this vector space that is contained in the is an isotropic subspace in general is a subspace of C4 that is contained in its orthogonal. And so the Lagrangian are the ones that have maximal dimension, in this case 2, complex dimension 2. So whenever we talk about Anosov representation, we define this representation in terms of a limit map. In general, it might not be easy to describe the limit map, but for Fuchsian representation is actually quite nice. In this case, it really corresponds to a Veronese embedding. So we have this smooth embedding. And so we have a smooth embedding into CP3 and another one into Lagrangian of C4 that we can describe concretely in terms of the polynomials, because you can take a point of RP1 and you can map it to the polynomial that has that root as a triple root. And in the case of Lagrangian, you send it to the Lagrangian that is generated by the same line, and the line that has that root as a double root. Like here I put X, I could have put Y, like they define the same Lagrangian. And so this map extend, like you can see the way I define it, I define in terms of root. And so it doesn't matter if my root is real or complex. So I just can extend this map to map from CP1 into the same space. This extension will not, we'll see how it comes out. But any question? Any question about that? Yeah, I will. I will explain. It's not obvious at all. We had no idea, but it really comes from what we found out is that there are exactly 4 lines that correspond to have a double root, and so these will be the 4 root or the full single root. It will define two tetrad. Yeah, but it's not obvious. It wasn't obvious to us, and we didn't know before. Yeah, we just did the calculation. Other question? Okay. So as I was saying, the first results, so I'll get back to Subhojoy, is like the new vibration that we define is really inspired by the SL2C orbit. So in fact, at the beginning, when we were trying to understand the fiber, we started looking at the SP4R orbit. Those are also, like actually the SP4R orbit are well understood. And there is a very nice picture that I might get to at the end. But unfortunately, that picture didn't help. So we could understand the topology of all the little pieces, but it was hard to understand how the different orbits would match together. And so that's when we started looking at this, and then this seems, help us. So if you look at the SL2C orbit, so again, how does SL2C act? SL2C acts on L by permuting the roots of the polynomial that you have. So that's why I'm defining the polynomial. It's the easy way to also define the action. And so we have 3 orbits, a closed orbit, which is the image of the C2 map. We have an open orbit that is the complement of the set KC. So the set KC is the thickening that we defined last time. And so this is the set, you take the union over all point in CP1 of this K C1T. So C1, this is a line, and so K of a line is defined as the set of Lagrangian that contain that line. So you are like the set KC is the set of all Lagrangian that contain a line with a triple root, triple complex or real. And then there is this intermediate orbit that is not open, not closed, okay? And so the main point of this proof is really the fact that this open orbit is identified with this ideal regular hyperbolic tetrahedra. These other two, the other two orbits are defined as their degeneration. And so their degeneration is CP2 times CP2. So on the diagonal, you just collapse to a point. Outside of the diagonal, the tetrahedra collapse to a line. So let's see how that goes, if the statement is clear. Yeah.
So the last time I wasn't understanding why you looked at this thickening.
Mm-hmm.
And so is the point here that in the background you already knew this slide, and so that's why you...
No, the thickening last time is because if you look, so first of all, yeah, the point of the thickening is double. So one is that if in this case you have a limit map into CP3, but we don't have a domain of discontinuity in CP3, and so in order to define a domain of discontinuity, I need to define the thickening. The thickening is a subset of the Lagrangian space, and is the set that you need to remove in order to have a proper discontinuous action.
That's what works. Why would you choose that thickening?
Oh, why would you choose that? That I think was the idea is like, how do you define a set? So you want something in terms of the limit curve, because the limit curve is where things goes bad. And yeah.
That's the psi one.
Yes, exactly. So,
but now you say, I don't want the psi one, I want something bigger.
No, because psi one is in a different space. We don't have a domain of discontinuity in that space. Right. And so the thickening is like how you define a set in the Lagrangian, that depends on the limit curve. Maybe you can do other things, but one natural thing is you have a line, you want to define something Lagrangian, well, let's remove all the Lagrangian that contain that line, because that line is problematic, and in fact, all these, yeah, so that's, yeah, of course. Other question? But yeah, this, I think it was the whole work, yeah, of Guichard and Wiener, then Kapovich, Liebenport, like this notion of thickening, this idea that you need to remove more. But yeah, thanks. Okay, so, oh yeah, so this is what I was saying before, is that thanks to this identification, then we can define a projection from the Lagrangian space into H3 bar by sending into the barycenter or the degenerate barycenter. Okay, so how does this identification goes? So actually, I'll discuss the fact that this complex thickening. So this is not what we are going to remove, because what we are going to remove is the real thickening, is a smaller set. But let's see why this set really correspond to CP1 cross CP1. So the way we are doing, we are defining this isomorphism concretely. And so I think for these results, the important point is this identification, because as we were saying, by the definition of this thickening corresponds to Lagrangian that contain a polynomial with a triple root, complex or real. And so if you do a calculation on how this Lagrangian look like, because being Lagrangian is quite restrictive, so what you can see is that these really correspond, like if a Lagrangian contain a a line with a triple root, then actually that Lagrangian has a common root. So all the lines will contain the root that we were having here. And so what you are going to do is that you're going really to define a map explicitly. And so like you want a map from 2 points in CP1 into this thickening. So what do? So if the 2 points are the same, then you just send it to the map that we defined before. So the Lagrangian that has that root as a double root, as a common double root. If they are different, what you do is that one root will correspond to this line with a triple root, and the other will just have the other as a double root and this as a common. Okay, and this map works. And in fact, with this map, we also understand the bad set. So this is the set that we will have to remove to get our domain of discontinuity. And so this is the set where the triple root is really a real root. So these are the Lagrangian that we are going to remove, that we will need later. And so for the complement, what we are going to do, like as I was saying to Subhojoy, like it's really a calculation. And so like what you do is that you take any Lagrangian. So in fact, like this is true just for any Lagrangian. Any Lagrangian contains a line with the double root. And so up to SL2C, like if your line has a double root, it means that it also has a single root. So I'm just choosing the double root to be 0 and the single root to be infinity. And so up to SL2C, we can suppose that this line here that we have is the polynomial, is the class of the polynomial x squared y. So then what we do? So then we study all the Lagrangian that contain that line, and all this Lagrangian is a CP1. You can write explicitly like it's the Lagrangian generated by this plus a x3 plus b y3. So and how you can complete this to a Lagrangian? Well, you can complete to a Lagrangian maybe with that, but this would be in the other set that we describe. So, or you can complete with Y3, but also that would be in the space that we defined before. But for any other way to complete, that will be a Lagrangian in this complement. So as long as this is not this triple root, like in this case, what really we do is that these L x squared y are really the Lagrangian parameterized by x squared y, bless you, a x3 plus b y3, such that this is in CP1. And the point is that we can use the last freedom on the SL2C action to choose this point to be the point 1, 1. And so this space is really the orbit of this Lagrangian. And so what we really do is that then we study this particular Lagrangian. And so if you study this particular Lagrangian, you can take the generic polynomial, the generic line that belongs there. And in this case, because we have polynomial of degree 3, you can use the discriminant to study how many points with the double root you have. And so you solve that equation and you find that there are exactly 4 polynomial with the double root. And if you look explicitly at the 4 double root, the cross ratio is really this cross ratio that is very particular, because it's the cross ratio that is the most symmetric cross ratio, and is the cross ratio that corresponds to maximal tetrahedra. And in fact, the same is true for the 4 single root. So one is a tetrahedra like that, and one is a tetrahedra that is opposite. And so this is basically all we need. Does this answer? Yeah. Any question? So now with this identification, we can describe this fibration easily, because so let's rewind a little bit. So we start with the Fuchsian representation, or Fuchsian representation in SL2R, SL2R inside SL2C, and then you embed SL2C in SP4C with the irreducible representation. And so in this case, the limit curve is really, first you identify the boundary with RP1, and then you use the Veronese embedding. And so our domain of discontinuity are all the Lagrangian from which you remove this set KR. And so like our projection that we defined before with this identification of tetrahedra really restrict to the domain of discontinuity to a projection into H3 union CP1 minus RP1. So like you should. So this is the line, this is the RP1 that you remove, that we remove. And so what we do is that we then do orthogonal projection into the H2. And so this defines a projection from our domain of discontinuity into H2. And this is the projection for which we study the fiber. So we study the pre-image of a point. So when you study the pre-image of a point, so you choose a point, let's choose the origin. Well, the pre-image under the orthogonal projection is the orthogonal line through that point that will intersect our sphere into 2 points. And so what we have is that we have our fiber really project to this closed interval. And in fact, we know exactly what's happening, because if we take a point in the interior, what does this fiber look like? I don't know, this is the projection. U was our projection from omega. And so if you have a point in the interior, what are you looking in F? You're looking at all ideal regular hyperbolic tetrahedra with this barycenter. And so what is that space? Is the whole SO3 mod this A4, because we have a 4 polynomial, but we don't have an order on the vertices. And so this is actually a famous cipher fiber manifold studied by Thurston, but like it's, yeah, the unit tangent bundle orbifold of this orbifold, S233. And then when you collapse to the, so you have these 3 manifold, when you collapse here, then this space collapse to these 2 sphere. And this is where, in this collapsing, this is where the singularity of this fiber comes into play, because now we have actually 4 points that are singular. And in fact, in this case, we understand the singularity. But yeah, it's like in one case, a point is, yeah, they are cone over length spaces. Anyway, so this fiber is really concretely defined And so it allows us to study the intersection form. Since it's not a smooth manifold, you cannot do the intersection form with homology as you would like to do. You really need to do with the definition with cohomology using the cup product yeah, it's a little painful. Like I think it's mostly the oddity that is hard. But any question about this? Okay. So, okay, this is what I was saying is like, okay, now go back to try to understand topology. We have our smooth vibration. We have these non-smooth vibration. And we have the two fiber that we know they are homotopic equivalent. So in order to study the topology of this fiber, it suffices to study the intersection form on this other four manifold, and that will allow us to understand the fiber up to homeomorphism. Like the theorem that we are using doesn't tell you anything about the diffeomorphism type. So like if we want to study the diffeomorphism, we would need a different idea. And so the cohomology in this case, like you can calculate the cohomology explicitly. In fact, Dumas and Sanders actually calculate the cohomology concretely. So they studied the irreducible representation, and so they calculated this cohomology in terms of like invariant coming from these flag spaces, this Schubert cell. Then we need to calculate the intersection form. And the way we do is that, yeah, we are using Meyer-Vietoris because this fiber has a symmetry, has an involution. And so we cover with two sets A and B that they intersect at a point in the middle that we understand. And then like we understand almost everything. The part that I think is hard is really understanding the parity. Like the fact that is rank 2 comes from the calculation of the homology. Signature 0 and the indefinite come from this involution of the fiber. But the oddity is the one that for a while we thought we wouldn't be able to. And then, okay, we were able to just do it concretely. And once we have that, like you see that your intersection form is this one, and the Friedman tells you that the fiber is CP2 connected, CP2 bar. Question. Is the fact that the four manifolds are classified by this intersection. Yeah, it's the fact that it suffices. Okay. Okay, so I'll discuss PSL3C. And in PSL3C, I'm planning to maybe discuss two cases, the irreducible embedding and the reducible embedding of SL2C. If we run out of time, I might skip one of the two examples and then discuss the last part, just to tell you a little bit. Okay, so in SL3, like here, and yeah, let me motivate this question. So the way I want to motivate is a question that I think is general, is interesting in general, and that I think is very little understood. Is when you have an Anosov component in the real character variety, it's unclear when you consider these inside the complex group. Do these components sit in the same Anosov component, or are these indifferent Anosov components in the bigger space? So I think this is in general hard, and this is the sort of baby example of this question. And so because our theorem, because as we have seen in our theorem, the topology of the fiber is constant on Anosov component, we were hoping, oh, maybe we study the fiber, maybe the fiber is different, hence we know these two different Anosov components in the real character variety do not belong to the same. Yeah, so we look at two ways to embed the SL2R in SL3R, one with the reducible representation with the block, and one with the irreducible representation. So these, the Anosov component is very often here called Barbeau-Fuchsian component, and the other is the Itchin. And so these are indifferent connected components in the real character variety. But it's unclear if they are in the same or in different connected component in SL3C, in the Anosov in SL3C. In fact, they are in the same connected component of the character variety. Okay, so we were thinking, okay, maybe we study the topology. At the end, it will not answer this because they will be homeomorph or diffeomorph. Okay, so let me describe these two maps explicitly. So again, we want to write these two maps in terms of polynomial because again, what we will define, we are going to define in this case as well a projection from the flag variety into H3 bar. In one case from the full flag variety, and in one other case from the domain of discontinuity. And so let me describe explicitly. So for the irreducible case, you see that the form of these two maps is very similar to the map that we described before. So you take a root and you send it to the polynomial with this double root, or the flag yeah, here I should, the way I wrote it is incorrect. This is the flag, is the flag generated by the first, is the pair, bx minus a y square inside the plane. So this is the one part of the flag, and this is the two part of the flag. And so, no, okay, sorry. Here I just wrote the C2. C2 is fine. Here I'm just projecting into the CP2 star. Okay, so here we are seeing the flag inside the CP2 times CP2 dual. Okay, so this is the first, and then the second is like the first map that goes into the first CP2, you send a point into the line that is generated by A, B, and 0, and the second is you add the point E3. So is the plane generated by this line and E3. And again, we define this thickening. And in fact, even in this case, there are various ways to define the thickening. So what you were asking also before is that, yeah, there are, this is one point also of the theory, is that you have different thickening that you can describe, and they give you different domain of discontinuity. Yeah. So here the thickening that we consider is the thickening for the domain of discontinuity in the flag. And so what we are going to remove, all flag, whoops, all flags. Yeah, again, like you think that one might learn. All flags such that either the line is equal to the C1 map or the plane is equal to the C2 map. So this is just one way to write together is that the Ci is contained between F1 and F2. And in fact, you can even decompose this KC as these two sets, where in this case F1 is equal to C1, and here if C2 is equal to F2. These two sets, like they are not disjoint. Is this definition clear? So what I was hoping is that to give you some concrete example, because I think sometimes this theory can remain very abstract, but working out some example, then you really make it much more concrete. Okay. Yeah, of course. These for us, yeah. Yeah, so again, this is like we just took the work of Guichard and Wiener, this work. And so they have just these combinatorics that I think again, as far as I understand, the way why they even thought about that is that, okay, what can you do when you have a map into like lines, a map into planes, what can you do? And so, and the Kapovich-Porty approach is more systematic. So you need to define more background to introduce because you need to discuss the balance ideal, and so some combinatorics of the Weil group associated. But with their approach, actually, they see a few more examples that Guichard and Wiener didn't see. So maybe to your question is that at the beginning, maybe they didn't see all of the possibility for the domain of discontinuity. But I think in general, even in their case, if you really try to work out some example, to really understand the whole domain of discontinuity is huge. There are just a lot of ways to do that. In the low dimensional cases, in many cases, it's doable. You look at they are a finite amount that you can work it out. But as long as you go to higher dimension, like you have really non-uniqueness. Yeah, of course. Other question? Yeah. Exactly, but the domain will be different because the map C1 and C2 are different. But the way you define it, yes, is the same. Yeah. Because in this case, both you are in SL3C, so there is one way to be Anosov. There is one parabolic, and so they are Anosov with respect to the same parabolic. And so this is why this domain of discontinuity, the way you define it, is the same. In general, if two representations are Anosov with respect to two different parabolic, the way you define is different. Okay, so this is the set in general, like the bad set, the set that we want to remove is the image under this map when here we have RP1. And so the domain of discontinuity that we want is when we remove this set. Okay, so now we are going to, in order to understand the domain of discontinuity and it's in the fiber, what am I going to do is that I'm going to try to understand better this thickening, this bad set, okay? And I need to do a different approach in the two cases because the two limit map are different, and so the way that the thickening works is very different. And so I'll do the reducible case because I think is way different than the irreducible one. The irreducible one that was like the ideas of what I will present is Dumas and Sanders work it out in the appendix to their paper. Is very similar, very similar to ideas that I discussed before. And so I want to discuss this case that is maybe more complicated, but different. Also because I think in general, reducible, the way when you define Fuchsian, where you embed with the reducible way, are in general less studied, less understood. And so it's, yeah, again, maybe more interesting. Okay, so here, what's happening, remember in this case, we are embedding like SL2, we are embedding with this block. And so our map, they okay, so what do? They define from a point, you go to this line, and then you complete with the E3 vector. And so what is, so this thickening is like either F1 is equal C1 or F2 is equal C2. So what does it mean? It means that either F1 correspond to the CP1 that is defined. So our C1 goes from CP1 into CP2. So it defines a CP1 inside the CP2. And so either the line belongs to this well-defined and particular CP1 inside CP2, or the plane contains this vector, okay? So these are the two sets, K1 and K2. And so in this case, we weren't able to define a projection from the full flag variety that restrict to omega, like we do in the irreducible case. But we were able to build a map from the domain of discontinuity directly. Okay, so let me try to explain what we are doing. Is that, okay, so we want to build a map from our flag in the complement. So here I'm doing everything over C. So this is smaller than my domain of discontinuity, but I'll show you how to complete that. Okay, so we go from our complement of KC into three, like here we have this CP1. We want to look at three distinct points in CP1. Okay, how do we define this point? I call this point X, Y, and Z. And so there are some, the first two are very natural. The last one is the one that is maybe more complicated, but okay, so for the first is like we have this special line, F1, and you look at the plane defined by F1 and E3, and you intersect with our CP1. And so this will give, so this is the CP1 where the third coordinate is 0. And so this will intersect at a certain line, certain. For the second, like we already have our plane, the F2. And so our F2, again, will intersect this CP1 at another point. The last one, I guess I used the wrong color here, is this light blue. The last one, there is a choice, okay? And we are making a choice on how to define that one. And the point is that what you do is that you look at vectors here. I'll do the three-dimensional picture in the next slide that maybe will help. But here is the cartoon. So here, like this is a dimension 2 Lagrangian. And so I have this point that is well-defined and this class in CP1. And so what you do is that you look at the area one parallelepiped. And so like you find a point that is the sum of x1, y1 and x2, y2, where the area is 1, and then you consider the plane generated by this point in E3, and you intersect with the CP1. So maybe let me try to see the three-dimensional picture. So, okay, so this is the CP1, the LC. So this is our LC, the CP1 that is chosen by our irreducible representation. Then what we have is that we have the line E3, and then we have the line F1. So what I try to do here, this red plane is the plane generated by these two lines. And so this plane will intersect my CP1 in this line. Then I have my other plane. And my other plane will, I think is this one, is black. I think, okay, this is my other plane that is F2. And so these will intersect in this other line. And this is the, like the other vector that we find, and so the other line that we find. Not sure this picture helps, but we are able to define this projection into, from omega into this triple. Let's see. So these are triple of distinct point in this CP1. So LC is a space in CP2 that is isomorphic to CP1. And so, and in fact, we can understand more precisely, what happens. So, like this, the way that I define it like that was from PC. So, remember, we have this set CR inside HCC inside of F. And so, associated to that, we have omega R. And these contain omega C. And so this is our domain of discontinuity. And so the map that I define to this smaller set. And so in order to define a projection from this bigger set, I need to understand how these 3 points, these 3 distinct points, they degenerate when I add this point, this more degenerate point. And so what happened is that here I was sending my flags into this map X, Y, and Z. And so what we have to study is that we have to study precisely like the points that are in here, that are not in here, and see exactly which one of these 2 points collapse. And that we have to do case by case. So there are actually five distinct cases, but the point is that, I'm not going into the details here, but the point is that we can extend these can be extended to a projection from our domain of discontinuity into, this was a projection into these 3 points. So remark 1, whenever you are in CP1 and you have 3 points, 3 distinct points, these give you a point in H3. How? Like you take the first 2 points, you take the geodesic between them, and then you do orthogonal projection of the 3rd point, and you choose. This doesn't look. So this is in fact the same as these 3 distinct points. They give you a point in H3 and a vector. They give you in fact a frame in this case. Okay, what we in fact find is that this map, this map extend. So this is see. So CP1 3. These really correspond to the frame bundle, the different F, frame bundle of H3. And you have a natural projection into H3 just by sending to the point. And what we do is that we can define the same. We can extend to the full domain of discontinuity. And then really define this projection into H3 union, again, CP1 minus RP1. And so in this case of the reducible setting, we define more generally, so these sit inside here, and so this full domain of discontinuity, then project into H3 union CP1 minus RP1. And so again, like we did before, then we can project down into H2. And this is the map, the non-smooth map that is the analog of what I described. Question? Yeah. Yeah, say one more time. The non-smoothness, it's not evident. And in fact, at the beginning, we thought it's like even in the picture before, like in the case that I described before, at least to us, it wasn't immediately clear that it wasn't smooth because, you define T2 tetrahedra. This is a barycenter. This is smooth and well-defined. And we thought that, but the point is that when you do this collapsing, so when the tetrahedra collapse, then that is where the non-smoothness comes. And here is something similar. So this is the part I didn't describe, but when you need to go from the omega C to the omega R, 2 of these points collapse. And this process, is not smooth at the point. So in fact, the singularity only comes in the pre-image, so in this case, we have, you project into these, again, H3 union CP1, you project down. So again, we have our fiber, that fiber over the interval. In the interior point, everything is smooth, is fine. The singularity now are here. Yeah, and another way to think is that for the fiber, the preimage of a point here is a cipher fiber manifold. So you have this exceptional fiber, and then when you collapse, some of these exceptional fiber collapse. And so that's where this singularity, that's why it becomes sometimes connected, like the singularity is a cone over lens spaces connected. So connected among lens spaces. Okay, so like as we were saying before, so in this case, actually, in the reducible case, the map here, is not a cipher file, is actually S3. But the way you collapse, you collapse. And in the extreme, you have this joint of CP1s. And this is believable if you think about this, our set, if you remember our set KR, we wrote as KR1 union KR2. And in fact, the CP1, one comes from this and one comes from this, but these sets are not disjoint. And so you have a lot. So like you have a lot, like here you have this disjoint. And so like here the singularity, like this is the bad singularity. And then we have other singularity at these two. Okay, so maybe I'll skip the irreducible case, but the irreducible case, like let me just draw the picture. Like in the irreducible case, what's happening with the analysis is that instead of like the generic point, instead of being tetrahedra for the irreducible case here, is that having two orthogonal geodesic in H3. So the space in the irreducible setting, like in this case, our fiber, what this space is SO3 mod. So this time we need to look at the group, the symmetries of these orthogonal geodesics. And so in this case is Z2 times Z2. And again, also here, like we have that at the extreme, we have this joint of two spheres. Yeah, it's like you can do things concretely in terms of roots. I want to spend the last part at least giving you the idea of maybe the first part of a general setting. But before I do that, any question? Okay, so just maybe this is the general idea is, so my PhD student, Mason, so he had two ideas. So at the beginning, I told him, it's like, so he wanted to work in this direction. And so there were a few other cases that we were looking at, like SPC, 6C, 6C. And so first he was looking at, but then one day he came, and so we had this idea of using circle action because I didn't discuss it here, but if you remember from our theorem, the structural group of our fibration is S1. And so there is a natural action of S1 on our fiber. Yeah, it's really the S1 coming from the PSO2. And is really coming from rotation, yeah. preserving the fiber. Okay, so like our fiber really comes with this natural circle action. And so he found this old, not so old, but older than what we were looking at, paper of Finn Tuchel, where he used circle action to classify simply connected four manifold. So one thing that I didn't maybe say out loud is that in all those cases, our manifold is simply connected. And so that is, yeah, is important here. And so Finn Tuchel classifies simply connected four manifold by the circle action by studying the fixed point of the circle action and the exceptional point. So fixed point, yeah, are points that are fixed. And so the fixed point, we will see that comes in two flavors. They are either fixed surfaces or isolated fixed point. And the exceptional point, what are those? So those are points fixed by a cyclic subgroup of S1. And so when you look at these set come with some nice invariant associated, like the fixed surfaces comes with an Euler class, and the isolated fixed point and exceptional surfaces comes with some cipher fiber invariant associated. That's the way that Finn Tuchel described. And so what he proved is that if you understand this locus and its invariant, that determine the four manifold. And so what Mason is doing is that he basically look at all, there are 6 cases where the dimension of the fiber is 4. Some are the cases that we describe, and there are a few more, 3 more. And the nice things, so there are 2 nice things. So one is that it doesn't have to calculate the intersection form, because already in this case, the intersection form is not a 2 times 2 matrix anymore, it's already a 4 times 4 matrix. And really understanding that, yeah, we didn't like. So we were very happy that he found this alternative way, because and so I think it's nicer. It's a cleaner, like, I don't know. It's a cleaner way to study the fiber. But the second point is also that, so Finn Tuchel didn't discuss his classification into the smooth category, because that's not what he was thinking. But actually everything that he is doing can be promoted to the smooth categories. Like you need to look at the invariant defined maybe slightly different in terms of tangent spaces. But yeah, that's what Mason is working on. And by reframing Finn Tuchel's work in the smooth category, actually he's able to study the diffeomorphism type of the fiber that we also weren't able to study. In the other cases, this is a work in progress. Whoops. This is mostly written, finished written. This is still only notes, but he then had a different idea in other cases how to study these fiber in terms of the thickening. And basically in this general part that I don't think I will for sure will not arrive to say anything, but what is finding is that the fiber is a sphere bundle over the thickening at a point, basically. Okay, so maybe in the remaining 5 minutes, I can tell you a little bit more about this first case and maybe tell you of the 6 cases, what are the 6 fibers, the diffeomorphism type. But before I do that, any question? Okay, so yeah, so what I was saying is that this classification comes in terms of these fixed point and exceptional point. Yeah, and these fibers are all oriented, which yeah is he needed. Okay, so fixed point is like yeah point that are fixed by the whole group, and exceptional point point that are fixed by some Zn, by some finite order point. What Fintuschel show is that every component of F is a closed submanifold of even codimension. And so like these fixed point, as I was saying, come in two flavors. Either there are isolated fixed point or they are fixed surfaces. In fact, these fixed surfaces are more annoying to calculate the invariant. And so in many cases, there are no fixed surfaces except in the some reducible case. But okay, and another thing that is important for the calculation is that the Euler characteristic of F is the same as the Euler characteristic of N. So yeah, I'm switching now and I'm calling the fiber N because F is the set of fixed points. So I apologize, I think, yeah. Okay, so what the Fintuschel, yeah, let me just try to tell you some of the important part that comes. And in fact, yeah, there are some things that we are just lucky. We are just lucky that the Poincare conjecture works in dimension 3. And so there are a sort of like good things that comes. Okay, so what we define here, okay, so here I didn't define, did I define it here? No. So N star is the orbit space of N. So N mod the action of S1. And so these, what Fintuschel proof is that this orbit space is a simply connected three manifold, and the boundary are really these fixed surfaces. And so because of that, and the Poincare conjecture of Poincare-Perman-Thurston theorem, then these three manifold it really look like S3 with some open ball removed. The second point is that he also showed that you always have a fixed point, and the set of isolated fixed point is finite. So you have only finitely many isolated fixed points. And finally, how does this exceptional locus look like? So the exceptional locus look like surfaces that connect. So we have some fixed point coming, isolated fixed point, and then the exceptional locus really look like a sphere that have this fixed point as their pole. And so in the orbit space, this sphere look like segment. And so this exceptional, or the closure of the exceptional locus is really looking like a polyhedral arc or a polyhedral curve. Luckily, in our case, in all the 6 cases that Mason analyzed, this is not a closed curve. Because if it's a closed curve, then you need to understand if it's knotted and which knot it is. In our case, is just an arc. And so, again, it makes understanding the topology much easier with the information that we have. Like, as I was saying before, like there are cipher fiber coming into the picture because okay, so these are our isolated fixed point, and these are the exceptional point. If you consider a neighborhood, a small enough neighborhood of the isolated point, like this is a cipher fiber sphere. So this is again something that you need to check. And so this is important in order to understand the invariant that you associate to each segment. Because what Tuchel need for his classification is these labels or these invariant. So for the fixed surfaces, you want an Euler number, and for the isolated fixed point and exceptional point, you want a certain cipher fiber data. Okay, I think I'm done, but maybe just so from this invariant, he's able to define easier invariant inspired by Young. What's happening is that in all these cases, he can really write it down, these exceptional locus, fixed locus, and this invariant by studying the action of SO2 on the associated flag spaces. So yeah, the 6 cases that we have are the Lagrangian space, the flag space, and CP3. With the embedding of the irreducible, or with the 2-block embedding, irreducible, or the block embedding in SL3C, or irreducible and 1 block and 1-1. And so maybe let me just say what the fiber are. So the one that we look was this one, and this is in fact the first case that he understood, where this is the connected sum, and these are how the other 6 look like. I apologize, and thank you very much.
Questions? So let's thank the speaker.